Good morning. Can you hear me? Okay, I'll speak conversationally. So I'm glad you're come to VMI to talk about these essential subjects in terms of the STEM fields. And of course, it's really a great pleasure to be welcoming you in the capacity as the Dean of the Faculty, because of course, I have 14 departments that produce majors, BAs and BSs, and I love them all equally. So devoting a couple days to the STEM fields appears to be a Sophie's choice for me. But I believe the two are very nicely linked, aren't they? And I think that if you judged your success as K through 8 teachers on how many actually entered the field that you were teaching, you'd be disappointed. If, on the other hand, you judged your success by shaping the mental terrain and the outlook of these kids early enough in life so they have the wherewithal to make choices when they become clear and apparent and feasible and before their eyes, then I'm sure all of you would feel very much different about your success. And so this is very much a matter of national security, is the alignment of our education system early in life so that when the opportunities present themselves in high school and college, they have the wherewithal to do it. How many folks enter into the math fields in their mid-20s without the proper background? Not only is it very difficult to do, they don't have the time to do it. They're in the middle of having to earn their livelihoods. So the other thing that I wanted to talk to you a little about VMI before I introduce our great guest speaker is VMI, many, many years ago, was the home of a great planetarium right near our library. And it was a place where I, as a 5 and a 6 and a 7-year-old, would go every Sunday and stare at the planets. And before my very eyes, at least in representation, I could see the birth, the adulthood, and the death of stars, and really planets, right before my eyes. And that image has stayed with me throughout my life, and I consider this to be an essential image planted in the heads of our kids, and you're a big part of that. Technology is not confined to the so-called STEM fields. Our first technologies were human language, and the language of humans gave way to the language of math, which began to uncover the secrets of nature, and that eventually has given way to the language of computers, and all 3 languages, and future languages as well, every adult needs in order to survive and prosper in the world in which we live today. So, to sum it up, I think this is a matter of not only national security, but the survival of the planet, the elements associated with biosphere, with ecosystems, with the Earth itself. This is a dangerous place to live, isn't it, as we've found out these last couple of days. Without your work early enough, we're not going to produce the scientists that help the humans prosper and survive over these next several millennia. So, now it's my pleasure to introduce the true guest speaker, Jeff Goldstein. He's the director. I agree. You should. Unfortunately, there are 7 more paragraphs to follow because he's got an impressive resume, but it's important that all of you can connect with a variety of things he's done already. He is the director of the National Center for Earth and Space Science Education, nationally recognized science educator and planetary scientist. He's dedicated his career to the public understanding of science and the joys of learning. As the center director, Jeff is responsible for overseeing the creation and delivery of national science education initiatives with a focus on Earth and space. These include programs for schools, families, and the public, professional development for the grade K through 12 educators, and exhibitions for museums and science centers. The center's programs embrace a learning community model for science and education. Dr. Goldstein oversaw the creation of the center's national science education initiatives, including the Student Space Flight Experiments program, which immerses hundreds of students across each participating community in every facet of real research. As director of the Voyage National Program, he led the organizational team that permanently installed the Voyage model, the solar system, on the National Mall in Washington, D.C. The exhibition is dedicated to an understanding of Earth's place in space, and now it's permanently installing replicas in communities worldwide. He is the director for the center's activities supporting NASA's Messenger spacecraft mission to Mercury, which includes establishment of the Messenger Educator Fellows, a corps of master's science teachers that are providing training for 27,000 teachers on solar system science and exploration content. He oversees Journey Through the Universe, a national science education initiative that engages the entire communities. He directs the Family Science Night program at the Smithsonian's National Air and Space Museum and is the principal speaker. The program's provided a school field trip designed for family learning after hours in one of the most visited museums on the planet. He's also a blogger on Huffington Post and writes Blog on the Universe. So please join me in welcoming Dr. Jeff Goldstein.
Okay, am I live? Can you hear me? So first of all, I wanted to thank General Smith and Colonel Gray for inviting me to be with you today. And what's nice is that I'm able to leave my normal world and be able to work with teachers like you. I think that's what's really important here is to recognize that every generation is a link in a chain. And every generation has to inspire and engage the next so that we can go where none have gone before. And what's really important to recognize are that teachers are what bind each link to the next. Because without teachers, we would not have a next generation to take on the mantle of the human legacy of exploration. So I also pointed out the other day that I think there are about 300 teachers here, which means that I'm probably talking to about 30,000 students a year, something like 30,000 students a year. So the leveraging potential is enormous. Let me also say something about science and STEM. This acronym STEM came on the scene a few years ago. Before that, nobody knew what science, technology, engineering, and math was in terms of a national initiative. What's interesting is that if you ask scientists and engineers, what is it that you do? Do you separate science, technology, engineering, and math? They would say, no, it's a seamless landscape. There's no way to separate one from the other. In the real world, STEM is integrated. It's in education circles where we have all of those disciplines and stovepipes, and what we need to do is break down those stovepipes and have teams of teachers working together. Let me give you an example. Math is taught in a very stovepiped way, where you've got math predominantly in math classes. Yet math is the language of nature. If you want to understand how she operates, you need to speak her language. And the fact that math is not taught as part of the language of all subjects in all human disciplines denies our students the ability to see. Again, math is the language of nature. It's not simply, it's like French or German. You can't imagine going and taking a foreign language class if you never have an interest in reading that foreign language or speaking to somebody in that foreign language. It allows you to communicate, and math is the same thing. So we stovepipe math, we isolate it, and that's unfortunate for our students. And it also leads to the notion that students will always ask, why do I need to learn this stuff? And the answer is because it allows you to see. So I thought what I would do is give you a sense of what it's like to do STEM in the real world, give you a sense of what we as a species of explorers have been able to accomplish, and hopefully set a tone for all of the wonderful concurrent sessions that are going on for the rest of the day. And I think a good place to start is with my favorite book. Has anybody read this book? I say, murmured Horton, I've never heard tell of a small speck of dust that is able to yell. So you know what I think? Why, I think that there must be someone on top of that small speck of dust, some sort of a creature of very small size, too small to be seen by an elephant's eyes. This is a wonderful book, but it's nonfiction. You might think it's fiction, it's nonfiction. And I think you'll understand why I'm saying this is nonfiction when we finish our visit together in a little while. Let me start by saying that I am an astrophysicist, and I get to study the universe. And my specialty is planetary atmosphere, so we're like interplanetary weather guys. And my friends and I had to build a very special machine called an infrared superheterodyne spectrometer. And we did that, yes, an infrared superheterodyne, that's also sounding like a Dr. Seuss book. An infrared superheterodyne spectrometer. We built it at Goddard Space Flight Center in Greenbelt, Maryland. And a few times a year, we would take this machine to the middle of the Pacific Ocean and cart it up to the top of a dormant volcano called Mauna Kea. And Mauna Kea, the summit of Mauna Kea is at 14,000 feet, so it's almost 3 miles into the sky. And so it is the highest point on Earth in the Pacific. There's actually a US Geological Survey marker near the United Kingdom Infrared Telescope that says this is the highest point on Earth in the Pacific. And I don't have that photo with me, but my friend Fred took a picture of me standing on that marker, and that was like Jeff on top of the world. And what's interesting is we use one of the most powerful telescopes on Earth. In fact, we've used a number of them up there. And we hook our spectrometer to this telescope, and the telescope points to a planet like Venus or Mars, or a moon of Saturn like Titan with a very thick atmosphere. And from 100 million miles away, we can measure gentle breezes of 2 miles an hour on that planet and build a global map of the entire circulation of the winds of that planet. And by looking at the family of worlds, looking at weather on the family of worlds, or volcanism or tectonic activity across the family of worlds, you get a better understanding of the physics, chemistry, and biology that gives rise to those global phenomenon. I could spend an hour talking about comparative planetology, but the reason I tell this story is because a number of years ago, a teacher came over to me when I was telling them about life on Mauna Kea, and she said, "Can you provide a sense of what it feels like to do science on top of the world?" And I thought about that very carefully, and I came up with a story that really is a story in 3 chapters. And so the first thing is that when you go to the summit of Mauna Kea, or when the puffy white cumulus clouds roll in, they roll in a mile below your feet. So you're like on a rock floating in the middle of the sky. And so here's the NASA Infrared Telescope facility, and those clouds are a mile below the summit. Anybody want to go, by the way? And when the sun sets, even in a dark site here on the surface of the Earth, away from city lights where you think the sky looks so phenomenal, at 14,000 feet when the sun sets, it's an unbelievable sight. 10,000 stars fill the heavens. And our city of stars, the Milky Way Galaxy, is this double band of white that just arches from horizon to horizon. And I guess the best way to really give you the emotional content of what it feels like is that you're standing on the top of the world in the Pacific, looking out into this vista we call the universe. And the only word in the English language that I've ever found that comes close to capturing that emotion is majesty. You're looking out into majesty. And what's also interesting about this is that you're not looking at it from the outside. You're part of it. It's part of you. You're the universe contemplating itself. Think about that. You're the universe contemplating itself. And then when you shift your gaze to the horizon, you see these incredibly powerful telescopes. And I think I have an image of that. So here are some of the telescopes on the summit. This is actually a few years ago. There are even more telescopes on the summit right now. So you shift your gaze to the horizon, and on the cinder cones, you see these remarkable machines of human exploration. And you recognize that standing on the shoulders of past generations, this is what human exploration looks like. These telescopes are peering to the depths of the observable universe and asking questions that have been asked for generations past, but now because we're standing on the shoulders of those past generations, because of a new conceptual way of looking at the universe or new technologies, we're getting to see things wholly new to the human race. And this second part, the second chapter of the emotion that washes over you, is the sense that you are part of a legacy of explorers, that you are attached to a legacy of human exploration, and you are now that next generation pushing the envelope. And the third level of emotion was a very personal one. And I had to build a special carbon dioxide laser that was ultra stable that allowed us to secure these wind speeds of a couple of miles an hour on a planet 100 million miles away. And this is a very persnickety instrument. It needs a very particular voltage applied to it. It needs the detector needs to be kept very cold. And in the middle of the night at 14,000 feet, when my friend was sitting at the control panel using a joystick to slew this massive telescope looking at Venus, and on the TV monitor there was a crosshair on this big image of Venus showing where we were measuring winds, I went over to my laser system and I was adjusting it, putting liquid nitrogen in the detector doer and making sure the voltage was right. And I just remember having this feeling, it's like, wow, this is like so cool. You're looking for the first time in human history at the winds above the clouds on Venus, and you started in Little Red Train Nursery School. I remember that so vividly. And I think the important point there is that when we are exploring on the frontier, we took a path to get to that place. And it started incredibly young, incredibly young. And the power of one is incredible. The power that lives in each of our children to take, for instance, the human race where we've never been before is incredible. And our kids need to be taught that. And my pathway from, excuse me a second, my pathway from Little Red Train Nursery School to the summit of Mauna Kea was empowered by my teachers. Without them, I could not have done it. And so I think that those levels of emotion are really important to recognize in terms of science. Because what I just described in terms of being on the summit of Mauna Kea and being overwhelmed with a sense of majesty, overwhelmed with a sense that I am part of a legacy of explorers, overwhelmed with a sense that I as an individual were able to contribute, that's science. And it's an incredibly emotional, joyous, human experience. And look, I don't wear a pocket protector. And so I wanted to set a stage for what science actually feels like, okay? And I would love to show you let's see if I have this video. Let's see, I have all the controls down here. Let me go to, wait a second. Lights, entry. Okay, this is the summit of Mauna Kea. Now what you have to realize is that this is a handful of stars in the Milky Way Galaxy, and virtually all of the stars you see have planets. And I firmly believe that next time you look up at the night sky, realize that somebody's looking back. And in fact, in their sky, we're looking at them. So that's the summit of Mauna Kea. And I think I can put the lights back on. Oh, Justin, thank you for showing me all this. Okay. So I think what I'd like to do now is get more into how this relates to education. And so I need to ask a question, why do we go to school? Let's look at the nature of human exploration. And I'm not, by definition, using science or STEM yet, okay? The nature of human exploration. So you're fifth graders. Boys and girls, why do you go to school? Because Mom says so. Any other reasons? It's the law. Socialization. What about in inner city America? Or very rural America? We eat. We're safe. I mean, there are two Americas. There can't be two Americas. There can't be two Americas. Not when it comes to our children, ever. What other reasons would a student give for why they go to school? I like some, yes, there's students that are going to say that, but what about the over the horizon look? Why are they ultimately going to school? To earn a degree and get a job and make money, and they can go and, go take their dates to a movie theater and eventually get married and be able to put a roof over their heads. And I claim none of that is why we go to school. At the most fundamental level, none of that is why we go to school. How many of you are parents? I'm a parent too. Do you remember that magic time when your children, as they were growing, they were first capable of expressing themselves and the unending stream of questions began? Everybody's giggling, right? Everybody's laughing about that because what I've just said is something so human, right? Everybody remembers that magical time when the unending stream of questions began. So they're, by definition, going to school. You know, a classroom is not a place, it's a frame of mind. And so here they are, perfectly capable of expressing themselves, and they start asking questions. Why? Why do we do that? Why are we asking questions as soon as we can? Because we are born curious. We are born to ask questions. We are born to explore. We're born that way. I don't need a teacher in a classroom to create that in children. They're walking into the classroom that way. And the way that we say it in education circles is that we are born inquiry-based learners. We are born inquiry-based learners. And as parents, we also remember that our infants love to poke their corner of the universe every chance they get. They explore near versus far and up versus down and color and texture. They love to poke their universe, and they're saying, hey, I want a response. And their corner of the universe will give them a response. And what they derive from this interaction with their world is that they start to understand how their world works. Aha, if I do this, this is the response I will get. The universe is giving them evidence. And they are interpreting that evidence. They're interpreting that data. And at a higher level, they learn that if I do this, the response might not be good for me, so let's not do that anymore. Which means that I learn how to navigate through my corner of the universe successfully. Which means that we are also born evidence-based learners. We require data of the world around us that we force to get. You know, we get that data, we force it on the universe. And we interpret that evidence to figure out how we navigate through the world in a successful way. So we humans are born inquiry-based, evidence-based learners. Does everybody understand that so far? Does that make sense? Now, if you switch to the opposite extreme and you look at professional scientists and professional engineers, researchers, and you ask them, what is it you do and get paid to do? They will tell you that they're in the business of organized curiosity. They're in the curiosity business. They ask questions all the time. That's what drives what they do, but they do it in an organized way. They ask questions in a way that have a higher probability of getting to an answer. They bring powerful tools to bear that have been honed over those generations past. But they're in the curiosity business. And they're also in the business of evidence-based learning, but for the entire human race. Because if a researcher pokes her corner of the universe in some brave new way, and sees some wholly new phenomenon never seen before by the human race, or maybe sees a phenomenon that has been seen but has never been understood before, and now bringing a new conceptual understanding to the table, she's able to explain it. Well, there's this emotion that washes over her, because she realizes that she's pulled back the veil of nature a little and seen something wholly new. She's the first. And after that, emotion washes over her and she kind of gets back to, okay, now the next thing I have to do is roll up my sleeves, because she has to write a paper. And she sends it into a journal. And if it makes it through the review board, because the review board feels that this is meritorious for publication, then it's published, and scientists and engineers all over planet Earth can see what she's proposing. And they have the ability to say, we don't believe you. And she has the ability to say, that's okay, because I told you how I poked my corner of the universe in my paper, so you go poke it the same way and see if you get the same result. Does everybody see what I'm saying here? So the point that I'm trying to make is that we are born inquiry-based, evidence-based learners, and scientists on the frontier, scientists and engineers on the frontier, are practicing inquiry-based, evidence-based learning, which means it is a continuum. It's a seamless continuum from birth to the frontier, which also means that our children are doing inquiry-based, evidence-based learning every day of their lives, because that's how they successfully navigate through their world on a daily basis. Now, the leap here is to recognize that inquiry-based, evidence-based learning is what we call science. That's what science is. And I'm not making a distinction between science and STEM, because by definition, science and engineering are STEM. You can't do one without science, technology, engineering, and math. It can't be done. And so inquiry-based, evidence-based learning is what we call science. And in fact, the process by which we do inquiry-based, evidence-based learning also has a recognizable name. It's known as the scientific method. And the scientific method is often taught very wrong, because we often teach it as a rigid recipe to follow. Do this, do this, do this, do this, which makes science boring, which makes science alien. It's like those kids aren't doing that on a daily basis through their lives. They don't recognize it. The scientific method is fluid. It is an art form. And those that practice inquiry-based, evidence-based learning are artists. And one person approaching the same problem may approach it differently than another person approaching that same problem, because it also brings the personality to bear. There are times when scientists and engineers, they don't even want to put a hypothesis forward, because they don't want to bias, they don't want to add a systematic bias to a pre-thinking on the problem. What they'll do is they'll say, hey, let's poke the universe and see what happens. That's a really powerful approach to science and engineering. Let's just poke it and see what happens. And so the scientific method is an art form. And the other thing that's really important here is that the scientific method is a misnomer. It's not owned by science. It's discipline independent, because inquiry-based, evidence-based learning works in every discipline imaginable. If an artist puts brush to canvas in a way that's wholly new, don't you think that they're doing inquiry-based, evidence-based learning to understand, well, if I try this color scheme, it might work, or this particular brush stroke? A poet that puts prose to paper in some fundamentally new way is using this process. A chef in a kitchen trying to work out a new recipe is using this process. This process should be, in my mind, embedded in history and art and science and all of the things that we teach. And what's interesting is that and let me see what's the next one. Yeah. So let me say that if we are going to prepare, so I'm making a transition here. So let me see if I finish out my thought on the last piece. I guess what I'm trying to say is that what we do in science and STEM grows organically from what it means to be human. And our children are fully capable of being immersed in that journey right now. And in fact, when you look at that journey, you need to recognize that it is not only interdisciplinary, it's got to be transdisciplinary. It's not just an integration of science, technology, engineering, and math, but you have to bring communication skills to bear. You've got to be able to write and research and work in teams. It really is a transdisciplinary landscape. And I firmly believe that we should be immersing students as part of STEM education in authentic experiences that mirror how scientists and engineers do their thing. And I think one motivation for that is to recognize that if we are going to inspire and engage America's next generation of scientists and engineers, which is critical for the future of this nation, we need to let them see it for themselves and stop teaching science and STEM as simply a book of knowledge. to recognize that the elements that need to be nurtured, that grow organically from what it means to be immersed in a real research experience, are ownership and learning, where it's the student's classroom and the teacher lights the way, critical thinking, problem solving, the ability to navigate an interdisciplinary landscape in order to secure core knowledge to solve a problem at hand, communication skills, and teamwork. And all of those things, by the way, are what scientists and engineers bring to their jobs on a daily basis, and it's what we should be immersing our students in at some level in the STEM curriculum, so that, as I said, students can see for themselves what scientists and engineers do. And I can tell you that ownership and learning and problem solving and critical thinking and that the ability to navigate that interdisciplinary landscape and communication skills and teamwork, those are the skill sets that a future employer is going to look for in prospective employees, regardless of what flavor of job is going to be available in 5 or 10 years. We don't have to identify the specific job that needs to be available to recognize that those skill sets are essential. And so my view, and this is a personal view, and you can put this in the circular file if you want, but I think that we're teaching way too much content. I think that there should be a higher focus on process and journey, on ownership and learning, and I think more importantly that testing has to serve education. Education can't serve testing. So people said, Jeff, well, you say it, but you need to walk the walk too. You can't just talk about these things. So, I built this program called the Student Spaceflight Experiments Program. We launched it in 2010. And a school district immerses 300 students in real microgravity experiment design and real proposal writing. And those students are broken into teams, and each team submits a proposal, and the proposals go through the same review process as professional microgravity researchers. And one of those experiments is selected to fly to the International Space Station and have an astronaut assigned to operate it as simply a technician. And we treat all of those students as real microgravity researchers. And this is quite remarkable to see what these students are capable of doing when we give them room to play. And so, by the way, we just announced Mission 10 to the International Space Station, which starts in February. So if your school district is interested in exploring coming aboard, talk to me. Let me skip that. So every journey has to start somewhere. And I say that not knowing something is a gift. So you tell me why. Not knowing something is a gift, unless it's the night before the exam, which is, okay. Well, why is not knowing something a gift? You're open because you can then. Every journey starts with a question. If you don't know something, it's a gift because you can ask a question and start a journey. That's what it's about, right? Every journey starts with a question. Go back to that unending stream of questions from our children. And so let's talk about the majesty of a question. And I was doing a training program at the National Zoo many years ago about inquiry-based exploration. And Roger Roscoe, who is a curator he's a curator at the National Zoo at the Reptile House. He said, Jeff, yeah, I know what you're talking about, because there was this one question when I was a little kid that just drove me. This one question, I wonder what's under that rock. He would go, I wonder what's under that rock. And he would empower himself to go up to the rock and lift it and see this brave new world of creatures that he never would have seen if he didn't ask the question in the first place, because they don't want to come out in sunlight. And so when he reveled in seeing these new creatures and a smile broke across his face, because that's what research feels like, what did he then do as a little kid? He said, I wonder what's under that rock, and this one over here, and that one over there. And I said to Roger, I said, yeah, I understand what you mean, because when I was a little kid, one of the questions that drove me is, I wonder what's in that rock. And I remember taking my dad's hammer and whacking rocks open in the backyard and saying, wow, there's this shiny, quartzy kind of thing inside this rock. And I know that there are friends of mine who are geologists, professional geologists, who said, that's exactly how I got involved in geology. There's another example of a question. Let's say it's a beautiful, cloudless day, and you look out into the distance and you're not obstructed by trees. You're looking out to the horizon. So my question to you is, how far can you see? How far can you see? I'm sorry, so this is a question. Let's see the power of a question. What? Anybody? This is an audience participation situation. 8 miles? 11 miles? How far can you see? I'm just asking, how far can you see? Which means what? Can you see the moon? That's 240,000 miles away. Can you see the sun? That's 93 million miles away. In the constellation of Orion, the hourglass-shaped constellation, the winter constellation, is very bright. You can see it from every, urban area on the planet. Okay? There's a star called Betelgeuse. You could see Betelgeuse with the naked eye. That's 500 light years away. A light year is 6 trillion miles. That's 3,000 trillion miles away, which means if it's 500 light years away, it took 500 years for the light to reach us. So what you're seeing happened 500 years ago, which means that it was packaged when Christopher Columbus set foot in the New World, and he said to his crew, "You see that star over there? The light packaged on that star right now will arrive in the early 21st century." You can even see the core of the Andromeda Galaxy, the next galaxy, which is 2 million light years away. You can see really far. Think about the majesty of that question. How far can you see? Is amazing. It's amazing. A question leads to wholly new places for a child, for all of us. Okay, now the next thing I think is important. By the way, is this helping at all lay kind of a foundation? So the next thing that's really important here is that the secret to journey, the secret to exploration, the secret to education is conceptual understanding at an emotional level. If you simply have your students memorize information that has no bridge to the familiar, no learning has taken place. In my mind, it's a waste of time. Okay? Conceptual understanding at an emotional level really means that you have an emotional response. And so if I tell you, okay, the sun is 93 million miles away, and then you give an exam, and there's a question on the exam saying, how far is the sun? And Johnny or Sarah kind of reach into their mind and they say, 93 million, and you give them an A. No learning has taken place because I don't know what 93 million miles is. It's a big number. And so there's got to be ways to build conceptual understanding at an emotional level. So let me give you some examples. And what I like to do is conduct what are called Gedanken or thought experiments. In German, it's Gedanken. You can learn a lot by experiments just done in your mind. So, and I forgot to bring in a piece of fruit. Okay. Does everybody see my orange? Does everybody see my orange? Okay, everybody close your eyes, and on the blackboard of your mind, picture an orange in the middle of that blackboard. Everybody raise your hands if you could see that orange. Okay, now put your hands down, and now erase the blackboard gently and imagine 2 oranges. How many of you see 2 oranges on the blackboard of your mind? Okay, now put down your hands, and now imagine 3 oranges on that blackboard. How many of you see 3 oranges sitting there? Okay, now one more time. Imagine 47 oranges. Not 46, not 48. Don't put them in special groups and columns. Okay? How many of you see 47 oranges? Alien. The aliens are among us. Okay? I counted 3 aliens in the room. What's the point of this thought experiment? If you can't visualize 47 of something, how can I take you into the universe and allow you to imagine 350 billion suns? Right? I mean, you have to be able to conceptualize things. Okay, so maybe there are some rules of the road. How far is your school from your home? What? 8 miles? Why didn't you give it to me in inches? I'm sorry? You don't want to do it in inches? 12 times 5280 times 8 is a little too much for you to visualize? Okay, how far is school? 25 miles. Somebody give me a different unit.
30 minutes.
30 minutes. Ah, time. 30 minutes. But wait a second, if you tell me 30 minutes, I don't know quite what that means unless I know what your mode of transportation is, right? Is that walking? Is that by car? If it's walking, okay. If it's by car, that's a reasonable trip for you, okay? But we use 30 minutes. Why didn't you give it to me in seconds? So one of the rules of the road is to build a bridge to the familiar and use small units, right? That helps us understand conceptually what we're talking about. So if I say it's a 30-minute by car drive, you conceptually understand, oh, that's not just around the corner. So what I want to do is take you into the universe using rulers, clocks, and models. 3 of the most powerful tools imaginable for conceptual understanding at an emotional level. So I want to make the universe accessible to you. Okay, and so what I'm trying to do is give you some sense of how you can secure conceptual understanding at an emotional level in science and STEM classes. And I'm going to use my playground as the vehicle because I'm an astrophysicist. Okay, so what I'm going to do is, first of all, oh, there's a word from our sponsor, is that right? This program is brought to you courtesy of past generations of inquiry-based, evidence-based explorers. That is absolutely true. And by Milky Way, the candy bar of choice from the Mars Confectionery Company. Okay, so anybody know what this is? There's somebody from Udvar Hazy here, correct? Doing a presentation? What is that? That's the Smithsonian's National Air and Space Museum on the National Mall. And I had the distinct honor of leading, as General Smith said, an interorganizational team to install permanently a scale model of the solar system on the National Mall, which is U.S. sacred ground. We had to go through the same approval process as the Washington we weren't around during the Washington Monument. The World War II Memorial, the Martin Luther King Memorial, we had to go through the same approval process. And so what I'm going to ask you is, can somebody tell me what the solar system is? What is the solar system? A group of planets. Okay, can you name some of the planets, by the way?
Yes.
And what would they be? I was going somewhere on Capitol Hill, and I went to a Capitol Hill security police officer, and I said, "Can you tell me? Do you know where whatever building it was?" He said, "Yes." Okay. Venus. So you're talking about not planets around other stars. You're talking about planets that are near and dear to our solar system. Is that right?
Yes.
Okay. So there are planets, and so what else is in the solar system? Asteroids, those big rocks between Mars and Jupiter. What's the largest asteroid, by the way? It's called Ceres. And if you wanted to gift wrap Ceres and give it to a friend, you would need a piece of wrapping paper 4 times the size of Texas. Now, if you've never lived in Texas, you really have no clue what I just said, okay? So asteroids, those big rocks mostly between the orbits of Mars and Jupiter. What else? Comets, which are big dirty snowballs, each one the size of, say, a city like Washington, D.C. And we now are pretty confident that in our solar system alone, there are enough comets to give 150 to every human being on planet Earth. One wiped out the dinosaurs 65 million years ago. Don't get in the way of a comet, okay? You're missing the big thing in the solar system. The sun, right? The sun is the mom or the dad, and everything else are the kids, and the kids include the planets. What's the planet we know and love? Earth, the big thing under your feet, right? The planets. What are going around the planets? Moons, that's part of the solar system. Asteroids, comets. And then there's this thing called Pluto, which is actually the first of the trans-Neptunian objects discovered by Clyde Tombaugh in 1930. He just didn't know that there were at least over 1,000 more. And so we know that Pluto happens to be the largest of those trans-Neptunian objects, but clearly it's different than the rocky planets, it's different than the Jovian planets, and that's why it's not a planet anymore. But Pluto doesn't understand why everybody's making the big deal over that. In 2006, when the International Astronomical Union changed the designation of Pluto, the Smithsonian called me up and said, hey, you got to come down to the Pluto stanchion down near the Smithsonian Castle. So I came down, and all of these people had left condolence cards. There were flowers. I mean, it was everywhere around Pluto. It was the most amazing thing. I called the Washington Post. They did a really nice article on it. And the one card that I really couldn't understand is there's this big card taped to the Pluto stanchion, and it was signed by all the other planets. And it said, "We still love you, Pluto." And I was wondering how, say, Jupiter and Saturn came to town without anybody noticing that. So that's the solar system. It's the family of the sun. And what keeps the solar system together? Gravity. Now, here's a trick question. How many stars are in the solar system? One. So what you're telling me is the sun is a star. The sun is a star like the stars in the night sky? All right, now listen carefully to what I'm going to ask. Okay? I'm not asking why, I'm asking how does it look different than the stars in the night sky? How does it look different? It looks bigger and it looks brighter. Now the question is why, and there are two possible hypotheses. One is it may be really, really close. Right, your thumb is certainly smaller than me, but if you put your thumb close to your eye and close one eye, you can make it look bigger than me because you can block me completely out, right? Easy way to show students that concept. What's the other hypothesis? Maybe it's just a big bright star. And it took the human race lots and lots of generations to figure out which of those hypotheses is correct. And we now know that the solar system, that the sun is really, 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 really close. You got it? Okay. So if we now go to Washington, D.C., so here we are in the nation's capital, just outside of the National Air and Space Museum. And I'm going, there's the Capitol Dome over there. I'm going to take this off because I want to reorient you. So here is the scale model solar system on Jefferson Drive, and there's the Washington Monument. So everybody imagine the continental United States in front of me. So here's the continental United States, a really big map. Everybody point to Washington, D.C. Everybody point to California. Good. So when we were building the model, we had an engineering sun because we wanted to figure out the texture. So this is the size of the sun. The scale model solar system is at the 1 to 10 billion scale, which means the real solar system is 10 billion times larger. Got it? And so this is the size of the model sun, a very large grapefruit, okay? And what I'm going to do is I'm going to ask for a volunteer somewhere in the side of the room. Come on up. Come on down. You're either loved or recognized or I don't know. And you are Justin. Okay, there's lots of Justins. Justin, it's Justin. Okay, so this is the model sun. Be very careful, it's hot. Okay? So here we are in Washington, D.C., in front of the Smithsonian's National Air and Space Museum. There is the U.S. Capitol. There is the Washington Monument. By the way, does anybody know what's on the top of the Capitol? What's that thing on top of the Capitol? Scaffolding. Well, yes. Yeah, he said scaffolding. Yes, but once you take the scaffolding away, what's at the top of the dome? A lady. And does anybody know the name of that lady? Her name is Freedom. And you know what her job is? She faces due east because her job is to greet sunrise on the United States of America each morning. And if you look westward over there, so there's the Capitol Dome, And over here is the sun, close to the east side of the National Air and Space Museum, and the Capitol Dome is on this side. And as you look westward towards the rest of the model solar system, you see an obelisk rising to 555 feet. What's that? It's the Washington Monument. And so I'm looking westward in this direction towards California. Okay? So now I'm going to give you a sense of the model solar system. So here is the model sun. And as I walk westward, I encounter Mercury and Venus. And about 50 feet west of the sun, I get to the Earth, which is right about here. And the Earth, the home of the human race with over 7 billion souls aboard, is smaller than the head of a pin. Okay, that's the home of the human race. And the entire orbit of the moon fits comfortably in the palm of a child's hand. That's the only place people have been so far. Has everybody got that? And this distance, what was that distance between the Earth and the sun? 93 million miles, but I don't know what that means. Okay, I don't know what that means, so let me see if I can make you feel it. So you're fifth graders, okay? Right? So boys and girls, is a commercial jet that you might take from a major airport to Europe fast? Anybody know what a typical speed of a commercial jet is, cruising speed? About 600 miles an hour is a reasonable speed. Depends on with the jet stream or without the jet stream. About 600 miles an hour. How much faster is that than the speed limit on lots of highways? It's about 10 times faster, right? 60 miles an hour, it's about 10 times faster. How fast is an Indy 500 race car? A little over 3 times faster than the speed limit. A jet is 10 times faster than the speed limit. Is that fast, boys and girls? Yeah, and if I could get into a jet and travel at the speed of a jet, if I could travel at the speed of a jet from the Earth to the sun, it would take 17 years to get to the sun. 17 years to get to the sun. Who's 10 years old? Play with me. Okay, now, okay, all right, wait. Here, this is really important. What I'm going to do is I'm going to ask who's 10 years old, and if you're 10 years old, because you want to play with me, I want you to keep your hands up, okay? Who's 10 years old? Now keep your hands up. Now I'm going to ask a really important question. Who's 10 years old and wants to do a math problem? Look what just happened. Did you see what just happened? You weren't reacting as 10-year-olds. You were reacting as you, right? And what's really, to be perfectly honest, that's sad that we are training our children, who then grow up into adults, to not like mathematics. Because the entire majesty of the universe was revealed by those who could speak our language. Math is incredibly important. And so some of you did not lower your hands. So who out there is 10 years old and wants to do a math problem? Raise your hand. Okay. It'll take 17 years to get to the sun. How old will you be by the time you get back? 27. And did you forget that it'll take you 17 years to get back? How old will you be? 54 or 44 years old? Boys and girls, you'd be 44 years old by the time you got back. Would you be an old person? Boys and girls, is the sun far? Yes. Didn't you learn anything? I told you the sun was really close. Are you feeling what 93 million miles means? 10 times faster than the speed of a jet, living in that plane for 17 years to get to the sun. On this scale, if the Earth is here, smaller than the head of a pin, our home, and I keep walking westward, I get to Mars and Jupiter, Saturn, Uranus, Neptune, and I'm finally at the dwarf planet Pluto, 2,000 feet from the model sun. I'm almost half a mile westward of the model sun, and I can just see, from a half a mile away, I can just see Justin waving. And there's the sun. And I'm looking across the planetary domain of our solar system. And I realize, from a half a mile down the street, the Earth, the home of the human race, is somewhere near Justin. It's just 50 feet from Justin. And on that world is a species of explorers with something the size of this that even has the ability to understand that Pluto exists. Pluto is a tiny little thing compared to the Earth. And from that distance, those creatures, that species of explorers, the who's and whoville, know that Pluto exists. That's a stunning statement. And on this scale, if I keep walking westward, I will get to a nearby, the nearest star. It's called Proxima Centauri, and it is on the California coast in Golden Gate Park. Does everybody hear what I just said? If the sun is a large grapefruit, the Earth is smaller than the head of a pin 50 feet away. Pluto is a half a mile down the street. And the nearest star to the sun is Proxima Centauri in Golden Gate Park, California. And that is the average distance of stars. That's a typical average distance of stars. And what do we call it when stars come together? Okay, so let's say you're all stars and you all have planetary systems. And what's your name?
James.
James is the sun, and James has the Earth. And you are all other stars. What do we call it when stars come together? A galaxy. And since this group of stars, this galaxy has James in it, the sun, this galaxy is the Milky Way Galaxy. And the two stars that we've talked about so far are the sun and Proxima Centauri. And that's an average separation distance. And there are enough stars in the Milky Way Galaxy to give 50 to every human being on planet Earth. 50 to every human being on planet Earth. And you know what's way cool about that story? I've only handed out one galaxy. One galaxy. In the tiny, insignificant sliver of the universe that we are allowed to see, which is called the observable universe, we now know that there are enough galaxies to give 50 galaxies to every human being on planet Earth. That is majesty. And it all came from generations looking upward and asking questions with something the size of this. And so, now one last thing. Let me do one more thing with Justin on the scale model solar system. So here we are in Washington, D.C. The nearest star, Proxima Centauri, is the size of a grape in California. What is the fastest thing in the known universe? Light, right? Does anybody know how fast it goes? 186,000 miles per second. I don't know what that means. In 1 second, it can go 7.5 times around the Earth. 7.5 times around the Earth in 1 second. Another way to say it, I work with the International Space Station folks, right? So I know a lot about the International Space Station. And so there's a real easy calculation that you can do just for things in orbit. If I walk slowly like this, the International Space Station is orbiting the Earth 40,000 times faster than this. 40,000 times, that's fast. It's a big number. I'm just trying to tell you it's a lot faster. Light is 40,000 times faster than the International Space Station. We have no hope for the foreseeable future of going anywhere near a tenth the speed of light. Light is incredibly fast. And so when we look at the sun, how long does it take light to get from the sun to the Earth? 8 minutes, which means you are looking back in time. It's a time machine. If you want to know what's happening on the sun right now, you got to wait 8 minutes. Okay? So here I am. That's the way it works. When you look up in the sky, you're looking back in time. If you look far enough out, you will see creation. Think about that. This is science fact. This is not science fiction. The farther out you look, the farther back in time you see. And so here I am at the sun, and the model Earth is how far away? 50 feet, right? So I am now model light. I am the most fantastically speedy thing in the entire universe, and I am going to leave the model sun and get to the model Earth in 8 minutes. Is this the speed of light on the scale? Too fast? Because I have to get there in 8 minutes. So how fast is the fantastic speed of light on this model? Is anybody old enough to remember Tim Conway and the old Carol Burnett show? The fantastic speed of light on the scale of the Voyage model solar system. You ready? The speed of light is 1 inch per second. It's the speed of a fast ant. Okay? The speed of a fast ant. So here I am on model light. In 8 minutes, where will I be? Earth. In 4.5 hours, where do you think I'll be? What's the farthest thing in my model? Pluto. In 4.5 hours, I'll be at Pluto. In 4.5 years, where do you think I'll be? California, which means that Proxima Centauri is 4.5 light years away. It takes light 4.5 years to get there, which means when you look at it, you're seeing what happened 4.5 years ago, right? Another way to say it is if I wanted to explore just the space between the sun and the nearest star to the sun at the fantastic speed of light, it would be like exploring the continental United States as a colony of ants. Did you get what I just said? Now, what I'm trying to do through this presentation is demonstrate how building bridges to the familiar lead to conceptual understanding, because you go, wow, there's some emotional understanding of what I just said. And models and rulers and clocks are very powerful ways to do that. Justin, thank you.
Oh, you're welcome.
So let me move on, and the other Justin in the booth, I am going to go through these slides. So let me go to lights, go to entry, and I've got the laser pointer of authority. And so let me just show you what I just talked about in imagery. When you go above Earth's atmosphere, you finally get to see the reality of the way we live, which is there's one star that's really big and bright. It's called the sun. And when you go above Earth's atmosphere, even in daylight, you can see the sun, and you can see that it's so big and bright, it's our star, we belong to it. And here is the sun, up close and personal with a lot of the light removed, and these are called sunspots, which are about the size of the Earth. So a good way to say it is 1 million Earths can fit inside the sun. 1 million Earths can fit inside the sun. That means a lot of Earths can fit inside the sun. But you see this star over here? Does anybody know the name of that star? This is Orion the Hunter. What's the name of that star? Betelgeuse. 800 million suns can fit in the star Betelgeuse. And Betelgeuse is not the largest star. And if you put Betelgeuse where the sun is now, it would swallow the orbits of Mercury, Venus, Earth, Mars, and Jupiter. Okay? So now let me go on to this next one. This is an image in high energy of the surface of the sun, and you can see that it's very dynamic, and these areas of flaring are causing material to move out into the space between the planets. When they arrive at Earth, for instance, they cause the aurora borealis and the aurora australis. And this area from which the flaring is taking place could swallow 100 Earths. Here is an image taken by the Messenger spacecraft as it flew by Mercury in 2008. And this was the side of Mercury the human race had never seen before. So this was history in 2008. We for the first time in history, saw this side of another world. And what's way cool about this photograph is you're in it. Look. It came from there. And this is Venus below the clouds. And since I'm running out of time, let me just kind of move on here. This is our home world. And you can see, what is the brown? Land, and the blue, water. And what's this white stuff? Those are clouds that they tell you there's an atmosphere. And this world is an incredible world. It is a spaceship with all known life aboard. All known life is aboard this spaceship right now. It's something worth protecting. And on this world, water and land and air conspire to give rise to life. The world is teeming with life, whether you're a bacterium in a drop of water, calling that drop of water your home, or you're a blue whale, where you're calling an entire ocean your home. This world is teeming with life. And this is an image of the continental United States, and here's California and the Baja Peninsula, the Pacific Ocean, and it's daytime in California, but you know that they are 3 hours behind us, and so it's nightfall in the eastern seaboard, and the entire eastern seaboard is lit up with lights from the human race. This is you at night. This is a picture of Mars. And I want to say that no discipline is an island, because life is, by definition, interdisciplinary. So let me tell you this story. Does anybody know what that is? It was hanging like this a few years ago, then it was restored, and now it's on display again, but laying down on a slight angle. What is that? That's the Star-Spangled Banner. And I used to live in a town called Upper Marlboro. And what's interesting is that when they were restoring the Star-Spangled Banner, we had built a prototype camera to be used on the surface of Mars, an infrared camera. And the Smithsonian asked us to see if we could image the Star-Spangled Banner in the infrared to identify contaminants that were embedded in the flag to help the conservators. So a Mars technology was being used to restore the Star-Spangled Banner. And I wanted to tell this story in education programs. And so I researched this, and lo and behold, I found out the town I lived in, Upper Marlboro, Maryland, was actually part of the story. In the year 1814, during the War of 1812, the British were in Baltimore, and they were told to pack up and come up. I'm sorry, I said that wrong. They were in Upper Marlboro, Maryland, and they were told to pack up and come to Baltimore. So the British did, they packed up, they went up to Baltimore, but there were 2 drunk British soldiers left behind, and an American doctor threw them in jail, got them arrested, and they were in jail. One of the British soldiers escaped and went up to the British in Baltimore and told them what had happened. So the British sent a detail back to Upper Marlboro to get the other soldier out of prison, and they did, and they arrested the American doctor and brought him up to Baltimore Harbor. And the Americans learned about this, so they dispatched a lawyer to Baltimore Harbor to, under a flag of truce, try to arrange for the release of the American doctor. But they were on a ship in Baltimore Harbor, and at that time, the American fort in Baltimore Harbor, Fort McHenry, came under intense British bombardment. And the American lawyer watched this and didn't know whether or not the American fort would hold through the night, but in the rocket's red glare, he saw this flag flying over Fort McHenry. And in the dawn's early light, the American lawyer saw this flag flying over Fort McHenry, and Francis Scott Key was inspired to pen the Star-Spangled Banner. That's why this flag is so important. Imagine if we could go back in time and tell Mr. Key that 162 years after he saw this flag flying over Fort McHenry, it landed on the surface of Mars. The American flag is on the surface of Mars. Look what we are capable of doing if we put our minds to it. Every generation grows old. And every generation reaches down to the next generation and puts them up on their shoulders and says, it's your turn to take us where we've never been. Those folks that hoist the old generation up on their shoulders, they're teachers. And that next generation takes us where we've never been before, and we have been doing this for a very long time. And this is just one of countless examples of what we can do if we put our minds to it. This is the Viking 1 lander at Chrysaor, Planitia, that landed in 1976. This is the Sojourner robot checking out a rock called Yogi. It landed in 1997. This is the Spirit rover on the surface of Mars, and I don't have a photograph, I left it out, of Curiosity, which is the latest rover on the surface of Mars. This is Jupiter. This storm on Jupiter is called the Great Red Spot. 3 Earths can fit inside that hurricane. This is not a color, this is not an artist's concept, this is a real photograph. This is the ring system of Jupiter seen edge on. This is a moon of Jupiter called Io, and there's an active volcano, and Io is so volcanically active it turns itself inside out every 250 million years. This is Saturn, taken by the Voyager spacecraft, and you can see the sun must be down here because the rings are casting a shadow on the clouds of Saturn, and Saturn is casting a shadow on the ring system. This is a photograph of Saturn, and that's the actual size of the Earth. That's the actual size of the Moon. This is the distance between the Earth and the Moon. The Apollo astronauts were simply going across the rings of Saturn. Saturn fits between the Earth and the Moon. You can't see some of the ring system over here. It just fits between the Earth and the Moon. And here's a Cassini spacecraft image of Saturn. Cassini is now almost 1 billion miles away, orbiting Saturn. It's a 3-story robot. And every day, from 1 billion miles away, there are images coming into Earth through the Deep Space Network. You can go to the Cassini website at NASA and see images that came in just a day ago. And so how much time do we have left?
30 seconds.
30 seconds. Oh. All right, can I tell a 1-minute story? Okay, a number of years ago, Gina Ross, the principal of Buzz Aldrin Elementary School, said, Jeff, can you come a week before the students arrive for the new year and talk to our teachers and get them really excited about human exploration and space and science? I said, Gina, sure, I could do that. And so I went over and I started talking to the teachers, and I was showing them a slide of Neil Armstrong and Buzz Aldrin returning from the surface of the moon. And in this, it was taken by Michael Collins, who was orbiting in the Lunar Command Module. And Neil Armstrong and Buzz Aldrin are returning from the surface of the moon. And in the top, you can see the Earth, so I'm in that photograph. And I was telling them that I got excited and inspired to become a space scientist in this moment of time in July of 1969, when I saw Neil Armstrong and Buzz Aldrin walk on the surface of the moon. I knew in that moment I wanted to be a space explorer because that generation inspired me. And I could go out at 9 p.m. Eastern Time from Uniondale, Long Island, and look up at the moon and realize there were 3 people 240,000 miles away. And so I was telling this story to the teachers at Buzz Aldrin Elementary School, telling them how I got inspired by my heroes. And the door opened in the back, and Buzz Aldrin walked in. Gina had invited Buzz Aldrin to his namesake school, and he sees this photograph, and he says, oh, that's me and Neil coming back to Mike. Like it was a family photo, you know? It's like this historic photo, and it's like, oh, it's me and Neil coming back to Mike. And I'm just beside myself. I'm trying to compose myself. My hero just walked into the room, and I'm trying to finish up this talk, and I managed to get through it, and he goes out into the hallway, and all the teachers go over to him to talk to him, and I'm packing up my AV, and I come out of the room, and he sees me, and he makes his way through the teachers, and he comes over to me, and he gives me one of those two-handed handshakes. And you know, it's like, yeah, you might not know somebody, but there's a connection. And so he's giving me one of these two-handed handshakes, and he says, Jeff, that was really, he called me Jeff. And he said, Jeff, that was really inspiring. Where did that come from? And I didn't think about it. I remember having a lump in my throat, and I looked him square in the eye, and I said what just came to mind. I said, it came from you. It came from you. Every generation has to inspire the next. And it is our charge as educators to inspire the next generation, because that's what this is all about. Education, teaching, is the noblest of professions because it empowers the entire human race. And what you do today provides ripples in time for generations unborn. What you are doing today to lay the foundation for the current generation will ripple through time to generations unborn. That's how important teaching is. So with that, I'm done.
Well, Jeff, thank you very much for your very inspiring speech, instruction, building bridges of the familiar to the future for our students. And please accept this small token of our appreciation on behalf of the superintendent, the staff and faculty, and the Corps cadets at BMI. Thank you very much.
Thank you so much.